So, a two-wheeled self-balancing robot, it sounds simple, I mean it's literally in the name, but turns out balancing is not as simple as it sounds. People have been trying to integrate self-balancing robots into our lives for decades, each one being more pointless than the next. But that being said, autonomous robots are just cool, and I want to make my own. So first, let's break down what we'll need to build this thing. Like all the robots in the channel, the project relies on a microcontroller, which instinctively I wanted to use an Arduino Nano, but they're actually quite shit. Most Arduinos, but specifically the Arduino Nano, has a single core 16 MHz CPU and up to 32 KB of memory. And for something to compare to, a similar microcontroller like an ESP32, which only costs a few extra dollars, commonly has a dual core 240 MHz CPU with up to 16 MB of memory, so there's quite a big difference. The only catch of the ESP32 is that it can only provide 3.3 volts to the GPIO pins, unlike the 5 volts that the Arduino Nano can provide to the GPIO pins. But fortunately for my case, that's just not an issue. The ESP32 could be slightly overkill for a project like this, I'm not sure, that's a lie, I actually have no idea, but I'd prefer that to an underperforming Arduino. Along with the microcontroller, we'll need a gyroscope, aka a position sensor, a couple motors and their drivers, a buck converter, and of course a battery. For the gyroscope, I'll be using the MPU 6050, which is generally the most common gyroscope and accelerometer you'll find for the size, price, and everything really. For the motors, I'm using NEMA 17 stepper motors with A4988 motor drivers. I'm using this particular driver just because they're really common and really cheap, and they can microstep plenty for what I'm trying to use it for. Now the reason I'm using stepper motors is because they aren't affected by the gradual voltage drop of a battery, which is a vital flaw for things like these projects, which you'll understand properly later. Another option such as standard DC motors are much easier to work with and they're a lot cheaper, but they are affected by the gradual voltage drop of the battery. For the battery and buck converter, I'm using an 11.1 volt 25C battery with just a random Chinese 12 volt buck converter I got off eBay. So chucking that all on a breadboard gets me here, but it's not really much use if it doesn't have a program. So most people with a fairly solid experience with programming would probably find this part piss easy, but to me and a lot of other people it's pretty advanced. For a program like this, we need complete control over the step motors, so using a library for the motors like Excel steppers is just out of the question. But I think I might be able to get away with using a library for the gyroscope and the primary program loop. Before going any further with the program, we have to do some theory. The self-balancing robot isn't just as simple as moving motors when the robot starts to fall. I mean, it sort of is. The robot works the exact way to something like a unicycle. When the unicycle is falling, the person pedaling pedals in the opposite direction to the way it's falling, and then it moves back up and balances itself. I don't really know how else way to put it, it's pretty simple. The only difference between a robot and a person with a unicycle is that the robot doesn't have brain and muscle memory. The self-balancing robot actually requires a pretty advanced program loop called a PID control loop. A PID loop is a controller used to autonomously maintain a variable around a set point. So in my case, it's used to maintain the actual angle of the robot close to the desired angle of 0 degrees. Now PID stands for proportional integral derivative, but before you get your panties tied in a knot, there isn't actually any calculus level maths involved in the programming of a PID loop. A PID control loop is its own whole thing, which I won't explain too thoroughly in this video. The important part for us is the three terms being proportional, integral, and derivative. Those three terms are what control how the robot moves and are represented in the code through gain variables, which we can change to control how much they contribute to the actual code and the balancing mechanism of the robot. The proportional term is responsible for adjusting the signal that's sent to the motors based off the proportional difference from the current angle, the actual angle, and the desired angle of 0 degrees tilt. So if the actual angle is really far in one direction, the proportional term will fire the motors to move the robot in the other direction, closing the gap between the actual angle and the desired angle. However, this often leads to the robot overshooting the desired point, leading to a little swaying loop back and forth, and it's not fun. And this is also the term that's by far the largest scale term of the PID. The integral term is used to eliminate what they call steady state error. And this is the gradual increasing offset of the actual angle from the desired angle, which just happens over time and is basically ignored by all the other terms, which eventually disorientate the entire system. The derivative term predicts and calculates the future behavior of the actual angle, effectively slowing the motors down if they're going too fast, too close to the desired angle, and speeding the motors up if they're going too slow, but going away from the desired angle, so if the robot was falling. This term is really helpful to help prevent overshoots, swaying loops, and it's just really useful to counteract unexpected knocks, like if you were to flick the robot. With that said, implementing this into an actual program is a whole nother story. First off, let's just clarify some things. All we need in this program is for the MPU 6050 to read the actual angle of the robot, and for the PID controller to correct that tilt by driving the motors and wheels. After testing all the parts individually and spending about a week on the PID, researching, testing, and some more like research, I found myself here. The program by all means is fucking terrible, and I highly don't recommend you take any notes from this, but it does work, sort of. A good thing to bring up again is the fact that I'm using an ESP32, which has a dual-core CPU, meaning that technically I can run 2 programs simultaneously. So with that in mind, here's what's going on in the code. So we're in the code and we start off with the libraries, and then we define the stepper motor pins, and then we make an instance of the MPU 6050. Then we set the PID variables, and the input is the current angle, so the actual angle of the MPU 6050 sensor, and the output is the calculated motor speed and direction of the PID of the motors. And then here we've got the PID gain control. So this is what we change. This is the variables that we change to change how the robot balances. And then here we've got the PID object, where we link it to the input, output, and the set point, which is all just in the documentation of the PID library. And then here we've got the timing variables, so that we can run the PID every 15 milliseconds. This one tracks when the PID was last updated, and then this one, the time between each PID loop. So the motor speed is constantly changing, that's just part of the PID. And then these two track the last time a step pulse was sent to each motor, which is, I don't really understand it. It's just what you got to do to make the stepper motors work. And then we've got the PID task handle, which is, it sets up the core. So it sets up PID to run on a specific core of the ESP32, which we specify later on in the code. So here we're declaring the 2 functions. So PID loop runs the PID calculations, and motor control handles the motor stepper control. So in the setup, we open the serial, and then we initialize the MPU 6050 I2 C address, I2 C address, and then we initialize the MPU 6050 and set it up, and then we have the stepper motor pins again, we're initializing them, and then we initialize the PID loop as well. And then here is where we specify what core we want the PID loop to run on. And we've set the PID loop on core 0. Now in loop, there's only one line, and we call the motor control function, which is down here. Now this is basically just a normal stepper motor control function thing, but it integrates the PID calculations into it. Now another function, PID loop, this one, it's a bit confusing. It's not actually called anywhere in the loop, it's called in the setup. So this function is constantly running in the background. So basically what's going on here is it reads the MPU 6050 and gets its tilt angle, and then this is a smoothing that happens, so it gets the reading from the MPU 6050 and it just smooths it out. It's just trying to artificially get rid of some noise, which it has the same effect as capacitors, which I've also got in the robot, which you'll see later. This isn't necessary. I don't even know if it's doing anything. I haven't really checked, but it works fine. This just calls the PID to run. It runs through a library, so it's quite simple. So this just calls it, and then it just does its own thing through the library, and then it just maps all the things with these variables so it can be used directly into the motors, which is what happens here. And this is what determines the motor direction. Here, it prints it to the screen, and if we wanted it to run all faster, I could just get rid of this, but I'll get onto that later. It might not even change anything, and that's the entire code. One thing I do want to mention though is that because there are 2 cores on the ESP32, core 1 is the default, so everything runs on core 1 unless you specify it to run on core 0, which is what I've done with the PID loop and the MPU 6050. So because we've called this line for the PID loop to run on core 0, it's going to run on core 0 constantly in the background, and the motor control are going to run constantly on core 1 because that's the default and we haven't specified otherwise. Now we're done, but we're not that done. We still have this one little itsy bitsy part that we have to work through. I still need to set the PID gain variable so it actually balances. But I'll get back to that super not so fun part of the project later. Now that I've got the working prototype here, I'm noticing it's just a quite bit too bonky, which is where PCBWay comes in. For the video and to use in the project, PCBWay sent me over this PCB to use in the video, and that one, and also that one as well. I didn't do a very good job designing the PCB, but they were happy to send me over a new one, I live in Australia, so the shipping's taken about 5 business days for each set of PCBs. Just the finish of the PCB is really well done. I was not expecting this, if I'm honest, but it's actually quite good. With it, I've soldered on these headers so I could keep it all modular, a makeshift battery terminal, a switch, and the micro stepping pads, which I forgot to trace back to power. But nonetheless, it all works and I'm really happy with it. So thank you, and check out PCBWay so you can get an awesome PCB like me. Okay, now the main build of the robot is a case way simpler than everything we were just talking about. I just designed a pretty simple shell and printed it in PLA Plus and got a few screws to mount it together. But when doing so, I put the battery at the top for a reason. When putting most of the weight at the top of the robot, it increases its center of mass and it makes the robot more sensitive to imbalance. Before this, I had it the other way around and it just wasn't a good time. I've joined the wheels to the motors through just a random coupling bracket, and I've tried to wrap electrical tape around the wheel as an attempt to increase the grip of the wheels, but I know this is a pretty shit attempt at trying to increase the grip, but I just could not bring myself to spend 30 bucks on rubber wheels, have to wait 15 years, and then redo the PID gain variables all over again. I just can't. Okay, so 2 things before we get started. And the first thing is, you're probably thinking, clean your room. The second thing is you're probably thinking that it's on carpet. Wouldn't that make it stand up easier than if it were to be on tiles? And my response to that is, fuck you, and I hate you're technically right, but also it mainly depends on how you tune the PID. If I put this on tiles right now, it just wouldn't move fast enough because it doesn't need to move as fast if it's on carpet. So it's a bit of a pain. I have to just put it up here and just let it, yeah, okay. Alright, so after I reset it about 3 times, it's all ready to go. Put it on the carpet. I've got these PID values. So you see that? That's just the effect. This is the effect of poor PID values. And that's just because I'm a nonce. But, so I'm just going to put it through a few tests and show you guys how it goes. It does loop a bit. That's just because I have shit PID gain variables. But if I nudge it slightly, other side, it does catch itself. Obviously, if I knock it hard enough, it'll fall. So it survives quick knocks alright. So if I... Hey, yeah. Just to rant on a bit more and waste your time. Overall, there has been a lot of noise going on with the MPU 6050 and drivers, and this has caused quite a bit of issue. It's causing an issue right now, so it spikes up and down. And I've tried to fix this issue with capacitors on the drivers and basically any power consumption, and it has fixed it a lot, along with the virtual smoothing in the program. It's still there, but it's not that obvious, and I don't think I can get rid of it. There are so many things that I can add to this project, like I can add a controller to change the PID values, which would make it a lot better and open up a lot more possibility for me to improve it. I can add Wi-Fi compatibility, and I can just use other parts to try and get rid of that noise so I can make it a bit more stable, because it's not very stable. And thanks for watching, and if we can hit 500 subscribers from this video, that'd be awesome. I love the support. Thank you guys so much. And if you're still watching, I love you. Thank you, and see you next time.